Welcome to rational functions. So a rational function is defined by a quotient of two polynomial functions. A function f of the form f of x equals p of x divided by q of x, where p of x and q of x are polynomial functions, with q of x does not equal 0, is a rational function. These are essentially the same as what we did last time with rational expressions. However, now we're essentially just setting y equal to them. So now we can graph it and see what a rational expression looks like as a function and as a graph. So one of the things they're going to ask you to do with rational functions is find the domain. So with rational functions, we have fractions, and we can't have our denominator be 0. So essentially, to find wherever x can't be, or wherever x can be, we have to find out what x can't be. And we can't divide by 0. So we're going to set the denominator equal to 0. So if we set x equal to 0, then we found out that x cannot be 0. So x cannot be 0, because if x was 0 here, it'd be 1 over 0, which is indeterminate. We don't know what that means. So x can be anything except 0. So on a number line, here we have 0. It can't be 0, so it's a big open circle. But x can be anything from negative infinity to positive infinity, with the exception of 0. So we can write that in interval notation as anywhere from negative infinity to 0. It's going to be open parenthesis because it's not including 0. And this is united with 0 to infinity. So that's how we would write the domain in interval notation. So another example of finding the domain. We still can't have our denominator be 0. So I'm going to set that equal to 0. So there's two cases where this will be 0. If x plus 2 is equal to 0, then that means x would be negative 2. So x cannot be negative 2, because if x is negative 2 plus 2, that's 0. It'll equal 0. And then there's another case where x is 3. If x minus 3 is equal to 0, then x is equal to 3. So it can't be positive 3 either. If x is negative 2 or 3, this would equal 0. So on a number line, we have the values negative 2 and 3. It cannot be those values, so it's an open circle. But everything else, x can be everything else in between and otherwise. So, writing that in interval notation, we start from left and go to the right. You have negative infinity to negative 2, not including 2, so it's an open parenthesis, united with, and in between, negative 2 to 3. So in between there, not including 3. And then united, everything from 3 to infinity. So this is what x can be. This is what x can't be, but this is what x can be. So here's another example. So we can't have this equal to 0 because we can't have an indeterminate form. We can't divide by 0. So we're going to set it equal to 0. We're going to factor this. So x squared plus 7x plus 10, looking at factors of 10, to add to 5, that's going to be x plus 5, x plus 2 is equal to 0. Setting these equal to 0, you're going to get x equals negative 5 and negative 2. Or rather, it can't equal those because then this will be indeterminate. This will equal 0. So on a number line, we have negative 5 and negative 2, and it cannot be those values, so it's an open circle. negative infinity to positive infinity. It can be anything except those values. So it's going to be anywhere from negative infinity to negative 5, open parenthesis, because it's not including 5, united. And then in between negative 5 and negative 2, it can be between negative 5 and negative 2, not including negative 5 and negative 2. And then from negative 2 to infinity. And that's how you write domain and find the domain of rational functions.